I talk about diffusion models for speech enhancement, and yeah, let's get started. So you probably heard about diffusion models already, and they have shown a very good performance in the generation of natural images. You may heard of models like DALL-E 2 or Stable Diffusion, and with them you can, for example, generate the Elbphilharmonie Hamburg as if it had been painted by Vincent van Gogh. And we find this quite interesting, and we asked ourselves the research question, can we also apply diffusion models for audio restoration tasks, and specifically for speech enhancement? And this question resulted in our work, which is called Score-Based Generative Models for Speech Enhancement, or SGMSE. And yeah, we published it as a conference and a journal paper, and I will basically talk about this today. So what is speech enhancement? For those of you who are not familiar with that, you have an input which is noisy speech. So it's most of the time a speaker talking into a microphone, and then this signal is overlaid by noise signals, for example, fabric noise or car noise or what have you. And then this noisy speech, which is typically in our task monaural, so you have only one microphone, fed into a speech enhancement algorithm such that in the end you expect to have the enhanced speech, which ideally is only in the signal of the speaker. All right, so now you know it's going to be about diffusion models and speech enhancement. So this is my overview of the talk. So first I start with the basics, and then I talk how we apply diffusion models for speech enhancement. I talk about alternative diffusion processes and how to combine predictive and generative models. I talk about causal processing. So if you would like to implement it in a real-time system, then you have to deal with causal processing. And in the end, I will present my work on audio-visual speech enhancement, and all these works have been published already. All right, let's start with diffusion models. So diffusion models are essentially generative models that aim at estimating and sampling from an unknown data distribution, P of X. And specifically, diffusion models define this process with a transformation between a complex data distribution and a tractable prior from which you can sample. And here, the physical concept of diffusion plays an intuition. So basically, you transfer from a tractable from your data distribution, which are the blue molecules in the water, to a tractable distribution, which is the uniform distribution here. And if you then are able to revert this process, you basically solve the problem of sampling from this unknown data distribution. So how does this work? So diffusion models basically consist of two stochastic processes. You have the forward diffusion process, which gradually adds noise to the data. Here we have an audio spectrogram. And then in the reverse process, we can generate new data by an iterative denoising procedure. So you start sampling from noise, and then you go back to your data sample. So here we work with continuous time diffusion models. So you can basically define the forward process as a solution to an SDE, and this SDE is described by a drift coefficient and a diffusion coefficient. The drift coefficient basically says where the diffusion process drifts to, so the evolution of your diffusion state xt, and the diffusion coefficient basically controls the Gaussian noise which you insert at every time of your process. And this diffusion coefficient controls the Wiener process, which has the property of Gaussian increment. So basically, every step you sample Gaussian noise and add it to your process state. Then you can show that you can also time invert this SDE, which results in a new SDE. And now we have it's called the reverse SDE, and we have a new drift term, which is the guy in the squared brackets. And you see that this new drift term contains the old drift term, the diffusion coefficient, and this so-called score function, which is the term in blue. And we again have the Wiener process, which is again controlled by the diffusion coefficient. But now this guy in blue is not tractable. So in high-dimensional space, it's very hard to compute that. And therefore, we use a DNN to approximate the score function, which we call the score model. So here you can see as a visualization how this whole thing works in a one-dimensional case. So we have a data distribution, a complex one. Here we have 3 modes. And then basically what you do in the forward process, you add more Gaussian noise such that you end up with a Gaussian distribution. And then this continuous process you can also discretize. So here you have a directed graphical model, and you can interpret it as a Markov chain. And then basically, if you discretize it in the reverse generative process, you sample this last random variable. It's just Gaussian noise, and then you apply every step in your Markov chain. You apply your score model as theta, and this score model is not only getting the current process state as an input, but also the noise schedule. And you can furthermore condition it on any kind of signal like text, audio, or what have you. All right, so that's basically the basics of diffusion models. Now I talk about how we use them for speech enhancement. So in speech enhancement, we have the following context. We always have paired data in the same domain. So we have the clean speech and the corrupted speech, and they both lie in the same domain, in the same space, so to say. And if you look at classical diffusion models, for example, DDPMs, then they have the following STE. And if you plot this for the one-dimensional case, then you see basically you start with a data point x0, and then you drift towards 0, and you add more and more Gaussian noise. But here you can see that it's also not dependent on y at all. And this is our proposal. What we came up with is to include this y into the drift term. And what you have now, in the forward process, you start from x0 and you drift towards y. At the same time, we add exponentially increasing Gaussian noise, which is shown by the gray shaded area. Also, you can see 5 sample paths that we have sampled. Now, the advantage is if we end up at y in the forward process, in the reverse process, we can also start from y. And y we have always available in inference. So y is the noisy speech. So that was the idea, and you can formalize it. So this process is called an Ornstein-Uhlenbeck process with a variance exploding STE. We call it Uwe, so keep this term in mind. So this is the baseline, and yeah, we will compare, we will see other processes later as well. All right, just recap, we have the forward STE, so we move from clean speech to corrupted noisy speech, and then we have the reverse STE with the trained DNN. And then to perform speech enhancement, we basically sample the first step, which is now centered around y. So we have y as an input, right? Like y is noisy speech. And then we solve this reverse STE with a numerical STE solver. And in our case, we take some kind of Euler-Maruyama solver. And then for 30 steps, we end up with a clean speech. Okay, so you know the theory now. Let's prove if it's also working in practice. So here we have the following experimental setup. We have 2 data sets, and I highly recommend to always test and train on different data sets because you want to show generalizability. So here we have the WSJ0 chime data set, which is a quite easier data set. So it starts from 0 dB SNR to 20 dB. So that means the speech is always louder than the noise. And we also use a standardized data set, the voice bank demand data set. And now we can come up with matched and mismatched conditions. So we have some kind of cross data set evaluation here. So we train in the matched case on WSJ0 chime, and we test on WSJ0 chime. So it's a matched condition, and we have the mismatched condition where we train on voice bank demand and we test on WSJ0 chime. So before I show you the values or the results, quickly, it's a lot of text on the slides. It's a bit, basically, we have 4 metrics to measure the performance. We have two metrics which are standardized by the International Telecommunication Union. So it's Polka and PEST. They both measure the speech quality. Then we have an objective measure for the intelligibility, so how intelligible is the sentence. And then we have one energy-based metric, which is just the ratio between the speech and distortion. And we have a DNN-based model, which is provided by Microsoft. And yeah, the first two, they provide MOS values from 1 to 5. And this one is from 0 to 1, but for all metrics holds the higher the better. So let's first look at the matched conditions. So here we have several algorithms, and I sorted them among the algorithm types. So we have generative approaches and predictive approaches. We will see a bit more in detail what that means, but for now, it's just important to understand that we have two groups of algorithms. And if you first look at the generative approaches, then you see that we outperform all methods and all metrics. And now if you compare to state-of-the-art predictive methods, then you see we are quite on par with them in some metrics like speech quality. Metric gun wins, and here conf-tasnet wins in intelligibility, whereas we again win in Polka, which is also quality measure. So it's always good to have a bunch of metrics to compare your methods with. But in general, we see that we are quite competitive with predictive baselines, and we outperform all generative baselines, which is nice. And now we can look, I think you can lower a bit, and then I go, yeah, thank you. And now we look at the mismatched condition. Here you see trained on voice bank demand and tested on WS0 chime. And now we can see the following effect, that in the mismatched scenario, we outperform all methods in all metrics, so also the predictive methods, which is very nice. And you can also plot the distributions, for example, of speech quality as violin plots, and these violin plots basically show the distributions over these MOS scores. And what you want to see is a very symmetric violin. So you have the matched case on the left side and the mismatched case on the right side. And so the distributions are a bit skewed always. That's what you expect, right? Like in a mismatched test scenario, you perform worse. But you can see that our approach, SGMSE Plus, is quite symmetric, whereas the other predictive baselines are more skewed. And this is basically quite nicely shows that we are more robust in unseen situations and generalize better. Then always important to also ask humans to rate your algorithms. And we did a small listening experiment with 10 participants and asked them to rate 12 random examples. And also you can see that our model in a matched and mismatched case was rated best. All right, so I showed you a lot of metrics, but yeah, judge for yourself. I will show you some audio examples. So I will first play the noisy input, and then I will play the output of a predictive baseline called conf-tasnet, and then I will afterwards play our output of SGMSE Plus.
Money managers who sell their firms but then continue working for them may be less dedicated under new ownership, they say. Money managers who sell their firms but then continue working for them may be less dedicated under new ownership, they say. Money managers who sell their firms but then continue working for them may be less dedicated under new ownership, they say.
So I think you might have heard that both methods perform quite well. conf-tasnet is a very good baseline. It was published in 2019. But maybe you also noticed that it still contains some speech distortions. It's better to listen with headphones, I agree. But I think I could still hear it a bit. And the generative method is known for really preserving this speech quality and do not distort the signal so much. I can play maybe another file.
Owens-Illinois said its share purchases would be financed by existing credit lines and new ones, double quote, to be arranged, period, double quote. Owens-Illinois said its share purchases would be financed by existing credit lines and new ones, double quote, to be arranged, period, double quote.
So especially when the noise is very loud, you can hear some speech distortions maybe. Yeah, because it's a masking-based approach, it's basically adding masks between 0 and 1. So you really hear these artifacts. And now let's listen to the generative approach.
Owens-Illinois said its share purchases would be financed by existing credit lines and new ones, double quote, to be arranged, period, double quote.
All right. So then we tried a different thing, namely there's not only additive background noise, but there's also convolvative noise. So we always have it, especially, for example, in this room, we have a room enclosure, so we have a lot of sound reflections, and these sound reflections result in reverb. And basically, how we model the reverb is we have the input speech X, and we convolve it with a room impulse response, and then we get the reverberant file. So now, in the training, we take the X0, the anechoic speech, so really like in a room without reverberation, and as an input we take the reverberant speech. We tried everything out, we had some experimental setup, and yeah, we also see that this method can deal with these distortions, which was very surprising to us, and that is not only limited to additive background noise. I can give you one example.
Analysts, too, generally played down the effect on banks.
Okay, where's my cursor? Oh yeah.
Analysts, too, generally played down the effect on banks. The company has 500 Japanese managers overseas, most of them in key positions, and expects the number to rise 60% in the next 5 years. The company has 500 Japanese managers overseas, most of them in key positions, and expects the number to rise 60% in the next 5 years.
All right. Yeah, you heard some examples from the WSJ0 dataset. It's Wall Street Journal articles read out. But yeah, that was basically our original work on diffusion models for speech enhancement. And then a colleague of mine continued this work, and he tackled some problems. I was also part of this work as a co-author. So yeah, we've seen the forward SDE for the UVE, so for the baseline, and now you can basically calculate the mean evolution of the process state. And this results in this linear interpolation. Interpolation is of exponential speed, as you can see. So I also plotted this here. So you drift towards the y, and you get less and less the speed. And the most crucial point is that you never reach y, because it's an exponential function, so it only asymptotically goes towards y. And this could be a problem, because in the forward process, so in the reverse process, we start sampling around y, but in the forward process, we end at a point which is not y yet. So we call this difference the prior mismatch. And for example, for the term we have used for gamma in this exponential function, we actually see we are quite far away from 1. So we are at 7.8. Maybe it's not correctly visualized here, but we are really not at y. And yeah, to solve this problem, my colleague had the idea to use a Brownian bridge drift term. So instead of this Ornstein-Uhlenbeck typical drift term, we now use a Brownian bridge drift term. We use the same exploding diffusion term, and we can see, so we call this, first of all, this SDE, we call it a Brownian bridge with exploding diffusion term. And if you now look at the mean evolution, then you see you have a linear interpolation of linear speed, and also for t equals 1, you really reach y. So we have no prior mismatch. And also another side effect, we get rid of hyperparameter gamma. And yeah, that's always nice for us machine learners to have less hyperparameters to tune. You can see also the mean evolution. So it is in dB. So do not get confused that it's not linear, but we have a logarithmic scale here. But you can really see that with the BBED, we reach the noisy speech completely, whereas for the UVE, we have this prior mismatch. It also results in a different variance term. We also plotted this here. So, and then we measured everything, and it's always nice when good theory also results in better practical metrics or better results. And yeah, you can see that, especially, for example, in the perceptual objective listening quality analysis, we get 0.3 beta, which is quite a good value for us. We can improve by more than one mean opinion square compared to the mixture. And also in the other metrics, we can show an improvement. All right, so yeah, I've talked about the basics, then how we apply diffusion models for speech enhancement, then just the BBED as an alternative diffusion process. And now I talk about can we also combine predictive deep neural networks with generative models. And this is basically the work of my colleague Jean-Marie. It's also a follow-up work, and it also got published as a journal, and I was grateful to be the second author. So here we come to the problem of what are actually predictive and generative methods. Some of you might heard the term discriminative models. I lean more forward to call them predictive models, because then it both holds for classification and for regression. But in general, what you have a training data set, you train your DNN, and then you have, for every input, you have a single deterministic output. So whenever you try to use the same input, you get the same output. And this output can also be described as the expectation of the posterior of x given y. So you always land in the mean of your data. And maybe some of you work with image data, then you have typically this over-smoothing effect, so you really do not get the high frequency resolution, but you smooth kind of like the image. And that's how you could think about this posterior, the mean of the posterior. Whereas for generative methods, the basic idea is that you do not learn the mean, but you really learn this posterior. So you can, every time you run your DNN, you can sample a new output of this distribution. And yeah, there's a reason why we have chosen this funny shape for the PDF, because that was the idea of my colleague. He said, this is a very far jump you have to do. Why can't you not first go to the mean and then use the generative model? Because you're closer to your goal. It's quite illustrative. I like that. And let's see how that works. So basically, we have the noisy speech, and we first use a DNN, which was just trained to predictively output the clean speech. We have this estimation x hat, and then we use this estimation at the starting point for our reverse SDE. So we add Gaussian noise, we run our reverse processed 30 steps, and we end up with our estimation. So let's see how that helps. And here on purpose, we have chosen SNRs, so a bit more difficult examples. They go below, and you will also see why we did that, because our generative model has sometimes problems with these inputs. It generates sounds which are not there actually in the signal. So I think you can lower a bit again. I try to. Here it really helps that we first have this predictive approach and then the generative approach. We have some values here which show that improvement, but also by listening, you really hear that these phonetic confusions which occur are significantly reduced. And with phonetic confusions, some people in the literature call it also hallucinations, especially, for example, in LLMs. For audio algorithms, I rather stick to other terms like generative artifacts or phonetic confusions. So these kind of distortions we can significantly reduce with this idea. All right, so I was talking about combining two approaches, and then we come to a crucial point. So my supervisor, my professor, he's from a signal processing background, and typically you apply these methods in telephony or, for example, in hearing aids. So devices which really require real-time processing. And all the works we've seen before do not work in real time. And why is that? Because basically the neural network sees the whole utterance. So it also has information about the future. So it's not causal, it's non-causal. And in this work, we try to tackle this problem to also make the diffusion models causal. And yeah, our main motivation back last year was the Signal Improvement Challenge from Microsoft. And this challenge focused on improvements in the speech signal quality. You can measure this with the signal metric, which is also, you see it's a standardized recommendation again. And also in this challenge, there were some other impairments you have to address. So not only additive background noise or reverberation, but also coloration. So if you have not so good microphones, or you have like some energy differences in the frequency bands with an equalizer, that's also part of the input data. Discontinuity, that happens sometimes if you use voice over IP. So if you, for example, have a video call with someone, then your speech is transmitted in packages, right? And sometimes just the network is jammed, or your computer loses the connection to your Wi-Fi. Then you lose some of the packages, and this will result in discontinuities in your signal. It's also part of the impairments. And loudness. Loudness is a big thing, so we always want to have a good loudness level. Right. And here comes the whole thing, why we were so motivated to implement this causal processing. Namely, they had a requirement, because it's Microsoft, they're interested in using it for their applications. So it should perform algorithmic latency and buffering latency less than 20 milliseconds. And they are also interested in super wideband speech. So before, all the examples were sampling rate of 16 kilohertz. So you only hear frequencies up to 8 kilohertz. And here we are interested in the full band that we humans can listen to. And so these are the two requirements. And our approach was basically to modify the network architecture, because the diffusion process itself, I didn't talk about it, is independent for each time frequency bin. So if we change the network architecture, the whole approach will be causal. And also, because it's a challenge, we had to, of course, look at the test set they gave us, so not the blind test set, and listen to what kind of distortions might be in there, and can we generate different data to improve our training. And right. So let's first talk about the modifications that we needed to make the whole thing causal. So under the hood, the score model is usually a UNet, and it contains some convolutional operations. And typically, convolutional operations are symmetric, so they also look in the future. So this is the output bin, so it also looks into the future. And this we are not allowed to do, right? Then we are not causal, we are non-causal. But how can you do that? You can basically shift the input and then cut afterwards. And this basically results that your convolution operator only looks in the past. So that's the first modification that we did from symmetric to causal. Then there are, at some layers in the UNet, we have attention mechanisms. We had to remove them as well because they are non-causal. Of course, we could also use mask attention, but we just removed it. Then we have normalizing layers, a big thing in neural networks to make them work properly. They are also global, so they look at the whole spectrogram, and we had to make them cumulative such that they only accumulate statistics over time. And we have the down and up sampling in the unit, for which we originally use FIR filters with consecutive conv layers, but now we changed to strided convs and transposed strided convs for down sampling and up sampling respectively. All right, so this is the exponential setup. We have clean speech, 48 kilohertz, noise, room impulse responses for the reverb, and then we simulated several corruptions, additive background noise, just adding up these twos, reverberation, convolve with the RIRs, clipping. Yeah, you just increase the amplitude and then you have a clip. Gain reduction, packet loss, you drop some packets, and lossy speech coding, which, for example, some of you might known for MP3, so some kind of codecs, which we also detected when listening to the test set. And also we listened that they do not only use the independent distortions, but also they chain them, so they consecutively use one distortion after the other. So for example, reverb, then noise, and then packet loss. Okay, then we evaluated everything. We only have the blind test set available because of the challenge. So we used a metric which is non-intrusive, so you don't need a reference here. So we can see here the MOS values for the signal quality and the overall quality. And yeah, you see an improvement. So that's what we did prior to the challenge evaluation. Of course, they will evaluate with real humans, but we want to see, are we already performing better on objective metrics we can use? And also in the other metric, you see we have a shift from lower MOS values to higher MOS values. And then, yeah, we submitted our files and, yeah, happily, like fortunately, we were ranked 5th in the subjective evaluation, and that's a really big thing for us because we competed with very big companies like Huawei, Microsoft, and Google, and we are, yeah, by far have less resources. And yeah, that makes us very proud, of course, and it's very nice to have this 5th rank. And yeah, I just don't want to talk about metrics anymore. I again want to really show you what the algorithm does. So we have a input signal time domain and the time frequency representation and the improved signal time domain. And yeah, you already see it has a limited bandwidth. It only goes up to 4 kilohertz. So it does not use the whole spectrogram, and it's clipped. You see really like the samples go, exceed this critical value of 1. So let's listen to it.
They titter loudly after they have passed by the ramifications of the...
Okay, my cursor is gone again. I know a trick.
Titter loudly after they have passed by the ramifications of the...
Yeah, you can really hear it extends the bandwidth, reduces the clipping, and you also see a generative artifact. So here's a gap, something happening here, and it really fills out something which is actually not really reasonable. Let's listen to it again.
Titter loudly after they have passed by the ramifications of
the generative model, I don't know, hallucinates, some people say, and yeah, does something. Okay, then we have another example, which is a very challenging example. You can already see, there's not really much speech in the beginning. Here you can see some speech information, and yeah, let's just listen to it.
That's pretty challenging.
And the output?
That's pretty challenging.
So again, you hear really these phonetic confusions. So it tries to in-paint something which does not exist. But the second part is, I would say, it's okay. I selected this, and let's look at another example. And here we have this thing I talked about before, the lost packages. So you see some gaps in the signal, also a limited bandwidth again.
I was wondering if you could tell me a bit more about what it's like to live and work there.
So you hear these clips because you cut the time domain signal, results in high frequencies. And let's listen to the output.
I was wondering if you could tell me a bit more about what it's like to live and work there.
So here really comes the point where a generative model shines, because they are generative, so they can really paint out or like fill out these gaps and recover or restore the original signal. All right. So that was our work on causal processing and the challenge submission. It actually, it really gives you a lot of impact, these challenges. Probably you know about it. Like really industry people really look at these challenges and see, okay, how good are the algorithms that exist at the moment. So this really helped us to have more visibility as our research group. And yeah, I can highly recommend to take part at challenges. But yeah, let's now look at audiovisual extension. It's actually my PhD topic. So I work on audiovisual speech enhancement. But yeah, as you know, sometimes you drift somewhere else, and was working a lot on generative models. But this is my topic where I'm into and where my supervisor expects something from me. So let's look at this challenging information, which I already said, like in very challenging scenarios where the noise is higher than the speech, so SNR is negative, then we may generate these speech-like sounds which really don't have a semantic meaning or sound like someone is muffling in the microphone. I can give you an example. So this noise file is quite noisy.
They were unbelievably expensive to administer.
This is the output, and I would like to you to pay attention to when do you understand something. So when is it intelligible? Can you really do the ASR? Let's see.
They were unbelievably expensive to administer. Can you remind me so very limited?
So in the first part of the utterance, you could understand something, and then the second part it gets confused. So it's not really sensible. So this is basically the motivation for our audiovisual work, because you can see that the vision modality can always act as a complementary input so that the world is inherently multimodal. So we always have different senses. We do not only hear someone talking, but he's also articulating, he has gestures, and of course also the mouth area. So the V-seams, the mouth shapes change when you talk, and they are consistent with what you hear with the phonemes. So let's listen to the example again.
They were unbelievably expensive to administer.
And let's listen to our audiovisual model.
They were unbelievably expensive to administer. They were time-consuming. They were limited to the local.
So here I would say you can more understand what's being said, and we can, before I show the results, I tell you how it works. So we have the diffusion model, what you have seen before, and what we do, we condition this diffusion model on the visual input, and for that we use a pre-trained self-supervised model called AV-Hubert, and we concatenate these features into the score model. So you have two models now. Here's how it works in detail. So you have the score model. For the diffusion process, you have AV-Hubert, which is basically a transformer encoder, and we take all the features from every layer and we sum them with a weighted sum. So it's also a trained block. We temporarily align them and we concatenate them to all the features in the encoder, to all encoder layers in the score model. Then the rest is the same. So we have noisy speech and the process state as an input, and you get the score. Right, and then we can test everything. We can do experiments with that. We use audiovisual data, LRS3, environmental noise. We have a bit more challenging scenario. This on purpose because we want to show that it works in very challenging scenarios. Then we have our audio-only baseline, which is really the same network architecture. And we have a state-of-the-art audiovisual approach and our standard metrics, quality, intelligibility, some energy metrics. And additionally, we also measure the word error rate of a downstream ASR system, for which we use an NVIDIA system. And then you can see in the speech quality, you gain a little bit, like a 0.2 with respect, or 0.15 with respect to the audio only. Intelligibility in this metric is not really improved so much. You can question this metric a bit, but then really if you measure the word error rate, you see we drop by 0.1 by 10, more than 10% from audio only to audio visual. And if you plot this over the input SNR, so on the left side we have very difficult examples, and the more you go to the right we have more simple examples, and you see for the simple ones all the models perform quite well. But then if you go to the extreme case, then you really see this big difference between audio only in orange and audio visual in red. And that's really what we also hear when we listen to the results. So I can play another file. I will first play the noisy, then the audio only diffusion model, the audio visual diffusion model, and then the clean file for reference.
We are talking about the venues in which those public spaces will come together. We are talking about the venues in which those public spaces will come together.
It's quite okay already.
We are talking about the venues in which those public spaces where we come together.
It's a bit more intelligible, I would say, and the clean for reference.
We are talking about the venues in which those public spaces where we come together.
So overall, we see an improvement in speech quality and speech intelligibility. If you take video into consideration, of course, you have to say there are some practical limitations. You do not always have video information available. It's more processing. So all these kind of limitations you still have if you would like to implement it in reality. But yeah, this brings me to my conclusions. So we developed diffusion models for speech enhancement, and we can show state-of-the-art performance in generative speech enhancement methods. And we show that we generalize better as predictive methods. And then we have worked on extensions. So we proposed some combination of predictive and generative models, which I personally think is the future. Then we have causal processing, which tackles the problem of implementing it in a real-world system. And last but not least, my PhD topic on audiovisual speech enhancement. Yeah, thank you for listening, and I'm open to answer any questions. You can also write me an email, of course. Thank you.
Thank you very much. We have 2 microphones. There is one in the back. I come here, maybe the feedback is a little less here. We have one microphone here, one microphone there. We're happy to hear questions from your side.
Thank you. This is what? Thank you for the very good talk and the very impressive examples. I have actually 2 questions. The first one regarding, since you start off with the noisy images, it seems that you get something like a conditional model out of...
A conditional model, you mean?
Yeah, exactly. Basically, no condition on what you observed. So could you still create unconditional samples with that, or is it always specific to one utterance?
So with this specific model we train, it's indeed we model the posterior distribution, so the condition on the noisy speech. And if you use no conditioning signal, then the model would not work as it works now. But you can train the diffusion model in the unconditional case. And then really it generates something which sounds like speech, but it's not intelligible. So it has no semantic meaning. But you can do that. Okay. And we have some work which actually needs to have this prior distribution. So if you think about posterior sampling with diffusion models, then you need to have this prior distribution learned. But with the models we have here, you cannot do that.
Okay, thank you. I was just wondering, can I also ask the second question? It was about the extension that you did with your colleague. When I was looking at the drift term, it reminded me a very lot on these optimal transport passes that you use for flow matching. So can you elaborate about the connection between these two?
Yes, so flow matching seems to be the new interesting thing out there. It's very well connected to diffusion models, I would say. I think you're right that the drift in, like, if you do the maths, that is also really linearly interpolating between initial condition and terminating condition. Yeah, I think yes, it's true. And my opinion on flow matching is I see some works, especially the meta guys, really push this forward. I think it's from them. I would really like to see the comparison if it's better than diffusion models or not. I have not really. Yes, it's very strongly connected, right? You have very similar ideas. Right. Yeah, that's an interesting paper for sure.
Yeah, thanks for the really impressive results. Can you say something about how the two approaches compare in terms of compute efficiency?
Yes, so here we really have, so compared to the predictive approaches, we really have like, for example, the conv-TASNet has around 8 million parameters. So let's talk first about memory. And our model has 65 million parameters. So you already have a higher memory requirement. And then because you have an iterative process, you have to call the network 30 times in our case. You have really much more flops you have to do. And I can give you some rough numbers. So if you were to compute with a predictive method as conv-TASNet, you have a real-time factor of like 0.01. So much faster than, so 1 second of file takes like 10 milliseconds. And for our approach, we are on a modern GPU, we are at around 1. So it's like a factor of 100. Yeah.
Thank you so much. It was really nice watching this result. I have a question. Is it possible, let's imagine someone that cannot hear but can see. Can you translate the audio into visuals that this person can see and understand?
Yes.
Do you think that is possible?
These works exist, so in both ways. So there are lip reading models, which really, so they work on a semantic level, but you have lip motions as an input and the text as an output, but there also exist synthesizing methods. So you have video as an input and the output is speech. It also exists, and they exist the other way around. So you have speech and you want to generate an avatar. And that's really what Meta is also very interested at the moment. So they have this idea of the metaverse, and they want to have like these characters, and you talk into your microphone, and then you see your avatar talking a talking head face, basically. So both tasks exist in the literature. I'm not super familiar with them, but I'm aware that they exist.
Based on the question just now, so with normal diffusion models for image generation, for example, right, we can condition these models by giving some further information to that model. In this case, you're kind of conditioning the diffusion model with the visual input, essentially.
Yes.
So have you tried or played around with the idea of just having pure noise with no recognizable human speech in the first place as an input for the audio, and the visual input being the speech, which would then ideally be pure like speech synthesis just from images? Like, does this work with your model? Like, have you played around with it?
Yeah, I have some examples in my mind where the noise is much louder than the speech, and then you see these generative artifacts that it kind of like around these energies in the spectrogram, it tries to generate some speech because the model maybe wants to impaint something or recognizes input energy as speech, which is not the case. But still, you have a little bit of speech there. So I have not experimented with only feeding environmental noise, but I would assume that it will generate these kind of muffled sounds or like speech-like sounds, but they have no semantic meaning.
Okay, so that means that your approach is not necessarily able to generate speech purely based on images with this method, so it's not competitive in that space.
Exactly, and one major point is really this conditioning, and what we condition on is also the noisy speech. So the network at every point sees the noisy speech, and it's a very strong guide. If this does not contain speech, I'm not sure.